For decades, we believed we understood how galaxies form. The process was clear, methodical, hierarchical. Small clumps of dark matter collapse first. Gas falls into those gravitational wells. The first primitive stars ignite. And over billions of years, through countless mergers and gradual accumulation, these proto-galaxies slowly grow into the massive spirals and ellipticals we see today. It's wrong. The James Webb Space Telescope just detected fully formed galaxies, massive as our own Milky Way, sitting in an epoch just 250 to 400 million years after the Big Bang. A cosmic infancy when they should not, cannot, and by every theoretical model we've built, must not exist. These red monsters are rewriting the timeline of cosmic evolution, shattering our models of structure formation, and forcing astronomers to confront the terrifying possibility that we never truly understood how the universe learned to build its first cities of stars. If you want to discover what happens when our most fundamental theories collide with impossible observations at the edge of time, hit that like button and subscribe. Prepare yourselves. Let's begin. On August the 27th, 2022, the world saw beauty in the first deep field images from the James Webb Space Telescope. Swirling galaxies painted in infrared crimson and gold, nebulae glowing with the fire of newborn stars, cosmic landscapes that looked like abstract art rendered across the canvas of space. Social media exploded with wonder. News outlets celebrated humanity's technological triumph. The public marveled at our ability to peer deeper into the universe than ever before, to capture photons that had traveled for over 13 billion years to reach Webb's golden mirrors. But in the offices and laboratories where astronomers had spent decades preparing for this moment, a very different reaction was unfolding. Confusion, then disbelief, then a creeping, unsettling dread. Because buried in the spectroscopic data flooding back from Webb's instruments was a pattern that made no sense whatsoever, a signal that contradicted every prediction about what the early universe should look like. The telescope was seeing galaxies, massive, luminous, fully formed galaxies shining brilliantly in an era when the cosmos was barely out of its infancy. The Fresco survey, one of Webb's flagship observational programs, had identified them systematically. Using the near-infrared camera, paired with its GRISM spectrometer, astronomers weren't just capturing pretty pictures, they were dissecting light itself, breaking it into component wavelengths to reveal the precise chemical signatures, distances, and ages of these ancient structures. The measurements were unambiguous. These galaxies existed at redshifts between 5 and 9, corresponding to a universe less than 700 million years old. Some appeared even earlier, in the first 400 million years after the Big Bang. To grasp why this is impossible, compress the universe's entire 13.8 billion year history into a single human lifetime of 80 years. In that timeline, these galaxies would be appearing when the universe is less than 2 years old. A cosmic toddler. An epoch when, according to Lambda-CDM, our standard cosmological model, the universe should still be fumbling with its first generation of stars, assembling small clumps of matter through gravity's patient pull, taking tentative baby steps toward structure formation. Instead, Webb revealed giants, galaxies containing hundreds of billions of stars, objects with stellar masses between 100 billion and 200 billion times the mass of our Sun. For reference, our Milky Way, a mature structure that has spent 13.6 billion years growing through mergers and gradual accretion, contains roughly 100 billion stars, These ancient behemoths matched that scale, while the universe was still in diapers. They had no right to exist, no pathway to formation under the physics we thought governed cosmic evolution. This wasn't a single anomaly that could be dismissed as measurement error or an exotic outlier. The survey had identified multiple examples. Dr. Mengyuan Xiao, lead author of the Nature study that unveiled these red monsters, captured the crisis with scientific restraint that barely concealed the underlying shock. Many of these galaxies were already mature in the early universe. This was not predicted by our models. That single sentence represents a seismic fracture in cosmology. When observations directly contradict fundamental theoretical predictions, something has to give. Either the observations are wrong, or the theory is fatally incomplete. Given Webb's instrumental precision, the multiple independent spectroscopic confirmations, and the consistency of measurements across different targets, option 1 is collapsing fast. The red monsters are real. Their name captures both their appearance, that deep crimson hue in infrared wavelengths caused by massive amounts of dust absorbing and re-emitting stellar light, and what they represent in our theoretical framework. Monsters that threaten to devour decades of carefully constructed cosmological theory. What makes these galaxies truly impossible isn't just size, it's efficiency. In standard galaxy formation models, when gas collapses into the gravitational wells created by dark matter, only a fraction of that gas actually converts into stars. The rest gets heated, blown away by stellar winds, or disrupted by supernova explosions and radiation from active galactic nuclei. This feedback acts like a cosmic thermostat, regulating star formation and keeping it relatively inefficient. In nearby galaxies today, the conversion efficiency sits around 20%. For every 5 kilograms of gas available, only 1 kilogram becomes stars. The red monsters were operating at 80% efficiency. They were converting nearly all their available gas into stars, at rates that should be physically impossible, given the feedback processes we know exist. It's as if the cosmic thermostat was broken, or more accurately, had never been installed. These galaxies were burning through their fuel reserves at breakneck speed, assembling stellar populations in a frenzied burst of creation that our models cannot reproduce even when pushed to their mathematical limits. The timeline problem compounds the crisis. To build a galaxy, you don't just need gas and gravity, you need time. Generations of stellar evolution are required. The first stars must form, live their brief violent lives, and die in supernova explosions that enrich the surrounding gas with heavier elements like carbon, oxygen, and iron. Those enriched clouds collapse to form the second generation of stars, which are more efficient at cooling and fragmenting into the stellar masses we observe. This process, repeated over and over through cosmic history, gradually builds complexity. Hierarchical assembly theory says small proto-galaxies form first, then merge together over hundreds of millions of years to create larger structures. It's a bottom-up construction project written in the language of gravitational dynamics and thermodynamics. Simulations running on the world's most powerful supercomputers, incorporating general relativity, dark matter physics, gas dynamics, and stellar evolution, reproduce this process beautifully. They show galaxies growing slowly, patiently, through cosmic time. And crucially, they predict that in the first 400 to 700 million years after the Big Bang, there simply isn't enough time for Milky Way scale galaxies to assemble. Yet there they sit, the red monsters, fully formed, burning bright, mocking our timelines. Their existence suggests that something fundamentally different was happening in the early universe. Some process our models don't capture. Some physics our simulations don't include. Some mechanism that allowed structure formation to occur at speeds that shouldn't be possible under the laws we thought governed cosmic evolution. Conference rooms fell silent when these results were first presented. Published papers suddenly required re-evaluation. Doctoral theses built on hierarchical assembly theory needed addendums acknowledging that the foundation might be cracked. For the first time in decades, cosmologists are using words they rarely admit in public. We don't know. We can't explain it. Not with minor parameter adjustments. Not with exotic but plausible scenarios. The red monsters represent a genuine crisis, a fundamental mismatch between theory and observation that demands more than tweaking. The James Webb Space Telescope had been designed to answer questions about the cosmic dawn, to illuminate the dark ages between the Big Bang's fireball and the first starlight. Instead, it generated the biggest question of all. If massive galaxies can assemble this quickly, this efficiently, this impossibly fast, what else have we misunderstood about how structure emerged from primordial chaos? To understand why the red monsters represent such a profound crisis, we need to understand what cosmologists expected to find when they pointed Webb toward the cosmic dawn. The predictions weren't guesses or hunches. They were mathematical consequences of Lambda-CDM, the Lambda Cold Dark Matter model, which stands as the most successful theoretical framework in cosmology's history. This model explains the cosmic microwave background radiation with stunning precision, predicts the large-scale structure of the universe we observe today, and accounts for how galaxies cluster across cosmic filaments. It's been tested, refined, and validated through decades of observations. Until Webb, it worked beautifully. Lambda-CDM tells a specific story about galaxy formation, a narrative written in the mathematics of gravitational collapse and thermodynamics. In the beginning, tiny quantum fluctuations during the inflationary epoch seeded slightly denser and slightly less dense regions of space. As the universe expanded and cooled after the Big Bang, these density variations became the scaffolding for structure formation. Dark matter, which interacts only through gravity and comprises roughly 85% of all matter in the universe, started clumping first. It doesn't feel electromagnetic forces, doesn't radiate energy, doesn't collide with itself. It just pulls, creating invisible gravitational wells that grew deeper over time. Normal matter, the protons, neutrons, and electrons that make up stars, planets, and us, initially moved with the dark matter in a homogeneous fog, but as dark matter halos collapsed and grew more massive, ordinary gas began falling into these gravitational wells. Here's where the process gets complicated and slow. When gas falls into a dark matter halo, it doesn't immediately form stars. It heats up from compression, reaching temperatures of millions of degrees. Hot gas doesn't collapse easily. It needs to cool down, radiating away its thermal energy through atomic transitions before gravity can compress it further into dense clouds where stars can ignite. This cooling process takes time, a lot of time. In the early universe, the gas is primarily hydrogen and helium, simple atoms with limited cooling pathways. The first generation of stars, called Population 3, had to form from this pristine gas, and theoretical models suggest they were massive, short-lived behemoths that burned through their fuel in just a few million years before exploding as supernovae. These explosions served a crucial function. They enrich the surrounding gas with heavier elements like carbon, oxygen, and iron, which are far more efficient at cooling gas through radiation. Each successive generation of stars made the next generation easier to form. But here's the critical constraint. This is a gradual bottom-up process. The Lambda-CDM model predicts hierarchical assembly, where small proto-galaxies form first in low-mass dark matter halos during the first few 100 million years after the Big Bang. These proto-galaxies are tiny by modern standards, perhaps containing a few million to a few 100 million stars, with stellar masses between 1 million and 10 million solar masses. They're chaotic, irregular, turbulent systems with vigorous star formation, but limited total mass. Over cosmic time, these small galaxies merge. When two proto-galaxies collide, their stars and gas combine, creating a slightly larger system. As hundreds of millions of years pass, then billions, these mergers continue in a cosmic assembly line. Small galaxies combine to form medium galaxies. Medium galaxies merge to create large ones. The Milky Way itself is the product of countless mergers. Its halo, populated with the remnants of smaller galaxies, it cannibalized over 13 billion years. Simulations incorporating Lambda-CDM physics reproduce this process with remarkable fidelity, showing how structure grows from small to large, from simple to complex, through gravitational interactions playing out across cosmic epochs. The timeline matters enormously. State-of-the-art simulations published before Webb's launch, using the most powerful supercomputers available and incorporating detailed physics of dark matter, gas dynamics, star formation, and feedback processes, made specific predictions about what should exist at high redshift. At redshift 7 to 9, corresponding to 700 to 250 million years after the Big Bang, the models predicted the universe should contain many small, low-mass proto-galaxies with stellar masses between 10 million and 1 billion solar masses. A handful of objects might reach 10 billion solar masses if conditions were exceptionally favorable. But galaxies with 100 to 200 billion solar masses, Milky Way scale behemoths, should be vanishingly rare or completely absent. There simply wasn't enough time for the hierarchical assembly process to produce them. The expected luminosity was equally constrained. Early galaxies should be faint, not because they're far away, though distance certainly dims light, but because they genuinely contain fewer stars, and those stars are forming from metal-poor gas at rates that feedback processes heavily regulate. The models predicted ultraviolet luminosity functions, statistical descriptions of how many galaxies exist at each brightness level that dropped off sharply at the bright end. You might find millions of dim proto-galaxies, thousands of moderately bright ones, and perhaps dozens of genuinely luminous systems. The extreme tail of the distribution, the brightest of the bright, should be sparsely populated if it exists at all. Efficiency was another key prediction. In modern galaxies, star formation efficiency hovers around 20%. For every kilogram of gas that falls into a galaxy, only 200 grams actually end up as stars. The remaining 800 grams gets heated by stellar winds, blown out by supernova shockwaves, or ionized by radiation from young massive stars and active galactic nuclei. This feedback is fundamental to Lambda-CDM galaxy formation models. Without it, simulations produce galaxies that are far too massive, with star formation rates that consume all available gas almost immediately, creating a universe that looks nothing like what we observe today. Feedback acts as a cosmic thermostat, keeping star formation inefficient and prolonging the assembly process over billions of years. Early predictions specifically stated that in the first billion years, feedback should be even more important. The first supernovae, exploding in low-mass dark matter halos with shallow gravitational potential wells, should blow most of the gas out of these systems entirely, suppressing subsequent star formation and keeping galaxies small. The process regulates itself. Star formation creates massive stars. Massive stars explode. Explosions eject gas. Gas loss stops star formation. The system pauses until gravity can pull more gas back in. This cycle stretches galaxy assembly across cosmic time. Then, Webb opened its eyes and saw something completely different. The red monsters weren't small proto-galaxies fumbling toward complexity. They were fully assembled systems with stellar masses between 100 billion and 200 billion times the Sun, comparable to the Milky Way. They weren't faint smudges barely visible in the data. They were luminous, dust-rich galaxies, shining brightly in infrared wavelengths, their spectroscopic signatures clear and unmistakable. And they weren't rare outliers occupying the extreme tail of some statistical distribution. The Fresco survey found multiple examples, suggesting these objects were relatively common in the early universe. Most damning of all, their star formation efficiency was catastrophically wrong. Spectroscopic analysis revealed these galaxies had converted up to 80% of their available gas into stars. 80%. 4 times higher than modern galaxies, 4 times higher than simulations predict is possible, even under the most extreme conditions. The cosmic thermostat wasn't just set too high, it appeared to be completely broken, or perhaps never installed. Feedback. The regulatory mechanism that keeps galaxy formation slow and inefficient in Lambda-CDM models was apparently absent or irrelevant in the early universe. The mismatch is stark. Lambda-CDM predicted small, faint, inefficient proto-galaxies gradually assembling through mergers. Webb observed large, luminous, hyper-efficient galaxies that appear fully formed. The timeline doesn't work. The masses don't work. The luminosities don't work. The efficiency doesn't work. Every major prediction about the observational appearance of the early universe, carefully derived from decades of theoretical development and computational simulation, collided with reality and shattered. This isn't a minor discrepancy that can be fixed by adjusting a few parameters or invoking plausible but exotic physics. This is a fundamental failure of the hierarchical assembly paradigm to describe what actually happened during the first few 100 million years of cosmic history. The reason we're only now confronting this crisis, only now discovering that our models of the early universe might be fundamentally wrong, is because we've never been able to actually look at the cosmic dawn before. Not really. Not with the clarity and precision required to test theoretical predictions against observational reality. The Hubble Space Telescope, despite its revolutionary contributions to astronomy over 3 decades, was hitting fundamental limits. It operated primarily in visible and near ultraviolet wavelengths, which meant the most distant galaxies were faint, reddened smudges at the edge of detectability. Hubble could see hints of the early universe, tantalizing suggestions of structure formation, but it couldn't penetrate deep enough into cosmic time to reveal what was truly happening in the first few 100 million years after the Big Bang. The James Webb Space Telescope was built specifically to shatter those limitations. Launched on December 25, 2021, and positioned at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth, Webb represents a quantum leap in observational capability. Its primary mirror, composed of 18 hexagonal segments of gold-coated beryllium, spanning 6.5 meters in diameter, collects nearly 6 times more light than Hubble's mirror. But size alone doesn't explain Webb's revolutionary power. The true breakthrough lies in what wavelengths of light it's designed to detect. Webb is an infrared telescope. Unlike Hubble, which observed primarily in visible and near ultraviolet wavelengths between 0.1 and 2.5 micrometers, Webb operates across a much longer wavelength range, from 0.6 to 28.5 micrometers, covering near-infrared through mid-infrared light. This isn't visible to human eyes. Infrared radiation lies beyond the red end of the spectrum our biology can perceive, carrying less energy per photon, but conveying information about colder objects and more distant cosmic events. For studying the early universe, infrared sensitivity is absolutely essential, and the reason involves one of the most important concepts in cosmology: redshift. When light travels through an expanding universe, its wavelength gets stretched. The photons don't lose energy to friction or absorption. They're literally being stretched by the expansion of space itself as they cross billions of light years. A photon emitted as ultraviolet light from a star in a galaxy, 13 billion light years away, will arrive at our telescope stretched into infrared wavelengths. The more distant the source, the longer its light has traveled through expanding space, and the more extreme this redshift becomes. Galaxies at redshift 7 to 9, existing when the universe was only 700 to 250 million years old, emit light that started as ultraviolet and visible wavelengths, but arrives redshifted into the near-infrared. To see these galaxies clearly, to capture their spectra and measure their properties, you need a telescope optimized for infrared detection. This is why Webb's design emphasizes extreme cooling. Infrared light is heat radiation. If the telescope itself were warm, its own thermal glow would overwhelm the faint infrared signals from distant galaxies, like trying to see faint stars while shining a flashlight in your eyes. Webb's 5-layer sunshield, each layer thinner than a human hair and deployed to the size of a tennis court, protects the telescope from the sun's heat while radiating the telescope's own warmth into space. The sunshield keeps the mirror and instruments below 50 Kelvin, approximately minus 223 degrees Celsius. The mid-infrared instrument, MIR-I, requires even more extreme cooling, operating at 6 Kelvin using a helium gas mechanical cooler. At these temperatures, Webb's own infrared emissions drop to negligible levels, allowing it to detect photons from the faintest, most distant sources. The discovery of the red monsters came specifically through one of Webb's key instruments, NIRCam, the near-infrared camera. NIRCam operates across wavelengths from 0.6 to 5 micrometers, straddling the boundary between the longest visible wavelengths and the near-infrared. It contains 10 detectors, each with 4 megapixels, providing both imaging and spectroscopic capabilities. For imaging, NIRCam captures stunning pictures of cosmic objects in multiple infrared filter bands, revealing structures invisible to visible light telescopes. But its spectroscopic capability, enabled by silicon grisms, proved crucial for identifying the red monsters. A grism is an optical element that combines a grating with a prism, dispersing incoming light into its component wavelengths while keeping the spectrum aligned along a specific direction. NIRCam's grisms are high-quality silicon transmission gratings that operate in slitless mode, meaning they can capture spectra from every object in the field of view simultaneously without requiring precise alignment of individual targets with entrance slits. This makes GRISM spectroscopy extraordinarily efficient for survey work. Point NIR cam at a patch of sky, insert the GRISM, and you obtain spectra for potentially hundreds of galaxies in a single observation. The spectral resolution is moderate, around R equals 1500 to 1600, but sufficient to identify characteristic emission and absorption lines that reveal the chemical composition, physical conditions, and crucially, the redshift of each galaxy. Redshift measurement is how we determine cosmic distance and age. When astronomers obtain a spectrum of a distant galaxy, they look for familiar features: hydrogen emission lines, oxygen lines, carbon absorption features. These spectral signatures have precisely known wavelengths when measured in a laboratory. But in the spectrum of a distant galaxy, these lines appear shifted toward longer wavelengths, stretched by cosmic expansion. The redshift factor, denoted Z, quantifies this stretching. A galaxy at redshift Z equals 7 has its light stretched by a factor of 8. Wavelengths are 8 times longer than when emitted. Using established cosmological models, we can convert redshift directly into distance and look-back time. Redshift 7 corresponds to a look-back time of about 12.9 billion years, meaning we're seeing that galaxy as it appeared just 770 million years after the Big Bang. The FRESCO program, the first Rayonization epoch spectroscopic complete survey, leveraged NIRCam's GRISM capabilities to systematically study galaxies in the very distant and early universe. FRESCO wasn't fishing for specific targets. It observed wide fields, capturing spectra for hundreds of galaxies simultaneously, allowing researchers to measure accurate distances and stellar masses across a representative sample of the early cosmic population. This systematic approach is critical for understanding not just individual exotic objects, but the statistical properties of galaxy populations, how common massive galaxies are at different epochs, how their number densities evolve, whether extreme objects are rare flukes or routine outcomes of early galaxy formation. When the FRESCO team analyzed their spectroscopic data, most galaxies fit expectations reasonably well. The majority were small, low-mass systems with stellar masses between 10 million and a few billion solar masses, consistent with hierarchical assembly predictions. But 3 objects stood out dramatically. Their spectra showed redshifts between 5 and 6, placing them roughly 1 billion years after the Big Bang. The spectral features allowed precise stellar mass estimates, and those masses were shockingly high, between 100 billion and 200 billion solar masses. These weren't statistical outliers at the tail of a distribution. They were objects so massive that Lambda-CDM simulations predicted they shouldn't exist at all at such early times. The GRISM spectroscopy provided additional crucial information beyond just redshift and mass. By analyzing the shapes and strengths of emission lines, like hydrogen alpha and forbidden oxygen, astronomers could estimate star formation rates and measure the efficiency with which gas was being converted into stars. The results revealed star formation rates exceeding 300 solar masses per year in some cases, sustained over timescales of tens to hundreds of millions of years. This isn't just rapid star formation. This is hyper-efficient conversion of available gas reservoirs into stellar populations at rates that feedback processes should suppress. The combination of Webb's infrared sensitivity, NIRCam's GRISM spectroscopy, and the systematic survey approach FRESCO created for the first time a true observational window into the cosmic dawn. Previous glimpses from Hubble and ground-based telescopes were like peering through fog. You could see shapes and outlines, but details remained frustratingly unclear. Webb ripped away that fog. It revealed the early universe in high-definition spectroscopic detail, allowing precise measurements of the properties that theory makes specific predictions about: masses, ages, star formation rates, chemical compositions. And what Webb revealed was a universe that doesn't match the predictions. A universe where massive galaxies assembled with impossible speed and efficiency. This isn't an instrument malfunction or calibration error. Multiple independent observations confirm the results. The spectroscopic redshifts are unambiguous. The stellar mass estimates, while subject to some modeling uncertainties, are robust enough that they can't explain away the factor of 10 discrepancy between observation and prediction. Webb's capabilities have finally given us the tool we needed to test Lambda-CDM galaxy formation theory against the actual early universe. And the theory is failing that test spectacularly. The red monsters are real. They exist in the data with ironclad spectroscopic confirmation, and their existence poses questions that existing models cannot answer. The most disturbing aspect of the red monsters isn't just their size or their premature appearance in cosmic history, it's how they built themselves. The spectroscopic analysis revealed something that shouldn't be physically possible. These galaxies were converting up to 80% of their available gas into stars. To understand why this number represents a catastrophic failure of our models, we need to understand the role of feedback in galaxy formation. In modern galaxies, star formation is remarkably inefficient. When a giant molecular cloud collapses under its own gravity, only about 20% of that gas actually becomes stars. The Milky Way, averaged across its entire disk, converts roughly 2% of its gas into stars per dynamical time, the time it takes for the galaxy to complete one rotation. This inefficiency isn't a bug in the cosmic code. It's a feature, a regulatory mechanism that prevents galaxies from consuming all their fuel in a single catastrophic burst and then going dark. Feedback processes act as cosmic thermostats, keeping star formation slow and controlled across billions of years. The feedback mechanisms are well understood. When massive stars form, they don't quietly burn their fuel. They blast their surroundings with ultraviolet radiation that ionizes nearby gas, heating it to thousands of degrees and making it difficult to collapse further. They generate powerful stellar winds that push gas outward at hundreds of kilometers per second. And when these massive stars exhaust their fuel after just a few million years, they explode as supernovae, and injecting enormous amounts of energy and momentum into the surrounding interstellar medium. A single supernova releases as much energy as the Sun will emit over its entire 10 billion year lifetime, but concentrated into a few seconds. That shockwave tears through molecular clouds, disrupting them, heating the gas, and ejecting much of it entirely from the galaxy. In low-mass galaxies with shallow gravitational potential wells, supernova feedback is so efficient that it blows most of the gas out into intergalactic space, effectively shutting down star formation until gravity can pull more gas back in over hundreds of millions of years. Even in massive galaxies where the gravitational pull is strong enough to retain most of the gas, feedback still regulates the process. It heats gas reservoirs, creates turbulence, injects metals that change cooling rates, and establishes a complex cycle where star formation triggers its own suppression. This regulatory feedback is absolutely fundamental to Lambda-CDM galaxy formation models. Without it, simulations produce galaxies that are far too massive, too compact, with stellar populations that consume all available gas within the first billion years. Early simulation attempts that didn't include adequate feedback mechanisms created a universe that looked nothing like reality. A cosmic landscape dominated by supermassive, ultra-dense galaxies surrounded by vast empty voids stripped of all their gas. Incorporating feedback fixed this problem. It made simulations match observations of local galaxies beautifully, reproducing their stellar masses, gas contents, star formation rates, and the complex relationship between galaxy properties and their host dark matter halos. The standard expectation, derived from decades of both observational studies and theoretical modeling, is that star formation efficiency should be even lower in the early universe. The first supernovae, exploding in the low-mass protogalaxies that form first in the hierarchical assembly picture, should easily eject most of the gas from these systems. The feedback should be overwhelming, creating a self-regulating cycle where star formation proceeds in fits and starts, never approaching high efficiency. Typical predictions suggest star formation efficiency in early galaxies should hover around 10 to 20% at most. The red monsters were operating at 80% efficiency. They were burning through their gas reservoirs at rates 4 times higher than modern galaxies, 4 times higher than theoretical models predict is possible even under the most extreme conditions. It's as if all the feedback mechanisms we know must exist — photoionization, stellar winds, supernova explosions — were simply absent or irrelevant. The cosmic thermostat wasn't malfunctioning. It appeared to have never been installed. Dr. Ivo Labbe, one of the astronomers involved in related early galaxy studies, captured the implication with stark clarity. These objects are way more massive than anyone expected. We expected only to find tiny, young baby galaxies at this point in time, but we've discovered galaxies as mature as our own in what was previously understood to be the dawn of the universe. The maturity isn't just about size. It's about how quickly and efficiently these galaxies assembled their stellar populations, converting their primordial gas reservoirs into stars at speeds that bypass all the regulatory mechanisms we thought governed galaxy formation. This efficiency crisis suggests that something fundamentally different was operating in the early universe. Either feedback mechanisms hadn't yet established themselves, requiring some cosmic time to turn on after the first generations of stars formed, or the environmental conditions were so different that feedback couldn't couple effectively with the gas. Perhaps the gas densities were so high, or the gravitational potential wells so deep, that even massive energy injection from supernovae couldn't disrupt the collapse. Or perhaps some entirely unknown physical process was at work, accelerating gas collapse and star formation through pathways our current models don't include. Whatever the explanation, the 80% efficiency of the red monsters is telling us that the early universe played by different rules than the cosmos we observe today. The red monsters aren't the only impossible objects challenging our understanding of the early universe. Running parallel to the crisis in galaxy formation is an equally disturbing mystery involving supermassive black holes. Webb has detected black holes in the early universe that are too massive, too bright, and appearing far too soon after the Big Bang to fit within our theoretical frameworks for how these cosmic monsters grow. In the local universe, there's a well-established relationship between supermassive black holes and their host galaxies. Nearly every large galaxy contains a supermassive black hole at its center, and these black holes follow a consistent scaling law. Their mass is typically about 0.1% of the total stellar mass of the galaxy's bulge. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million solar masses, while our galaxy's total stellar mass is around 100 billion solar masses. The ratio holds across thousands of galaxies, suggesting that black holes and galaxies co-evolve. Their growth intimately connected through feedback processes, where the black hole's energy output regulates star formation in the surrounding galaxy. Webb is finding black holes in the early universe that completely violate this relationship. In some galaxies existing just 400 to 600 million years after the Big Bang, the central black hole contains 10% of the galaxy's stellar mass, not 0.1%. That's 100 times higher than the expected ratio. These aren't slight deviations. These are black holes that appear to have outgrown their host galaxies by orders of magnitude, reaching supermassive status when their galaxies are still relatively small, star-poor systems. The problem is growth time. Black holes grow by accretion, pulling in surrounding gas and converting about 10% of that mass into energy through radiation as matter spirals into the event horizon. This radiation creates pressure that pushes gas away, establishing the Eddington limit, the maximum rate at which a black hole can accrete matter before its own radiation halts further infall. For a black hole starting from stellar mass origins, perhaps 100 solar masses formed from the collapse of a massive star, growing to 1 billion solar masses while respecting the Eddington limit requires hundreds of millions of years of continuous efficient feeding. The timeline doesn't work. Some of Webb's discovered black holes have masses exceeding 10 million to 100 million solar masses, while existing in an era when the universe was only 400 to 500 million years old. Even if these black holes formed immediately after the first stars at 100 million years post-Big Bang, and even if they fed continuously at the maximum Eddington rate without interruption, the mathematics doesn't allow them to reach observed masses. They're too big, too fast. This has forced theorists to consider exotic formation mechanisms. Perhaps some black holes didn't form from stellar collapse at all, but through direct collapse, where giant primordial gas clouds, never fragmenting into stars, collapsed directly into black holes, weighing 10,000 to 100,000 solar masses from birth. These heavy seeds would have a head start, potentially explaining why supermassive black holes appear so early. Webb has identified candidate objects that might represent this direct collapse process in action, including a possible intermediate mass black hole caught in the act of formation. If confirmed, these observations would validate a theoretical pathway that until now has been pure speculation. Alternatively, perhaps the Eddington limit isn't as strict in the early universe as we think. If the gas supply is sufficiently dense and chaotic, black holes might feed in super Eddington bursts, temporarily violating the theoretical speed limit through brief episodes of hyper-efficient accretion. Or perhaps primordial black holes, formed in the first seconds after the Big Bang through quantum fluctuations, rather than stellar processes, seeded the growth of supermassive black holes, giving them a primordial head start before the first stars even ignited. What makes this black hole crisis particularly relevant to the red monsters is that both phenomena point toward the same conclusion. The early universe was far more efficient at building massive structures than our models predict. Whether forming supermassive galaxies or supermassive black holes, The cosmos in its first few 100 million years assembled complexity at speeds that shouldn't be possible under standard assumptions. Something about the conditions, the physics, or the processes operating at cosmic dawn allowed structure formation to bypass the regulatory mechanisms that slow growth in the modern universe. When headlines scream that the James Webb Space Telescope has broken cosmology or disproven the Big Bang, they're both right and profoundly wrong. Understanding the distinction is crucial to grasping what's actually happening in astrophysics right now. The Big Bang theory itself, the fundamental framework describing how the universe began in a hot, dense state 13.8 billion years ago and has been expanding and cooling ever since, remains absolutely intact. What's collapsing isn't cosmology's foundation. It's one specific story we built on that foundation, the hierarchical model of how galaxies assemble. Lambda-CDM is a framework with multiple layers. At its core are predictions about the universe's large-scale structure, its expansion history, and the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. These core predictions have been tested with extraordinary precision. The Planck satellite measured the CMB's temperature fluctuations to within parts per million, and those measurements match Lambda-CDM's predictions with stunning accuracy. The distribution of galaxies across cosmic filaments, the ratios of hydrogen to helium formed in the first few minutes after the Big Bang, the accelerating expansion driven by dark energy, all of these remain consistent with observations. The crisis lies one level up in the theoretical hierarchy, in our models of structure formation, specifically how gas collapses into dark matter halos, cools, fragments, and forms stars. This is astrophysics, not fundamental cosmology. These processes involve messy, complicated physics, turbulence, magnetic fields, radiation transport, chemical evolution, supernova explosions, black hole feedback. Unlike the clean mathematics of cosmic expansion governed by general relativity, galaxy formation involves thousands of interacting physical processes that we model with approximations and simplifications. The red monsters and the supermassive black holes are telling us that our astrophysical models, our approximations for how structure forms, are wrong or incomplete for the early universe. They're not saying the Big Bang didn't happen. They're not contradicting measurements of the CMB or the expansion rate or the abundance of light elements. They're saying that when gas fell into dark matter halos 400 million years after the Big Bang, something happened that our simulations don't capture. Some process operated with far greater efficiency than our models predict. This distinction matters because it defines the scope of the crisis. We're not facing a revolution comparable to the overthrow of Newtonian physics by Einstein's relativity, where fundamental laws had to be rewritten. We're facing something more akin to realizing that our weather prediction models are missing a crucial atmospheric process. The foundation of fluid dynamics and thermodynamics remains valid, but our specific implementation needs revision. Several possibilities are on the table. Perhaps the initial conditions for galaxy formation were different than simulations assume. Most simulations start from simplified density fields at redshift 100 or so and evolve them forward. If the actual distribution of matter and the properties of the first dark matter halos were more complex, that could accelerate structure formation. Perhaps cold dark matter physics itself has subtleties we haven't included, particle interactions or clustering behaviors that enhance collapse rates at high redshift. Or perhaps the gas physics was radically different. In the standard picture, gas cools slowly through atomic transitions, and that cooling time sets the pace for star formation. But if the early universe contained more molecular hydrogen than we think, or if metal enrichment happened faster through some early population 3 stellar generation we haven't detected, cooling rates could have been dramatically higher, allowing gas to collapse into stars much more rapidly. The feedback question looms largest. If stellar winds, supernovae, and radiation pressure didn't effectively regulate star formation in the early universe, if the cosmic thermostat truly hadn't turned on yet, that would explain the 80% efficiency of the red monsters. But why would feedback be absent? Perhaps the first galaxies formed in such dense environments that even massive energy injection couldn't blow out the gas. Or perhaps the initial mass function of stars was different, producing fewer of the massive short-lived stars that generate most feedback. What's clear is that Lambda-CDM as a cosmological framework describing the universe's expansion, composition, and large-scale structure remains robust. What's failing is our specific implementation of galaxy formation astrophysics within that framework. This isn't semantic quibbling. It's the difference between rebuilding a house's foundation and redesigning its interior layout. The foundation, the Big Bang, cosmic expansion, dark matter, dark energy, shows no cracks. The interior, the detailed story of how matter assembled into galaxies, needs to be redesigned from scratch. Faced with observations that fundamentally contradict predictions, astronomers are proposing several competing hypotheses to explain how the red monsters assembled so rapidly. None of these explanations is fully satisfying yet, and each raises as many questions as it answers, but they represent the cutting edge of attempts to reconcile theory with Webb's impossible observations. The first hypothesis centers on hyper-efficient cooling. In standard models, gas falling into dark matter halos takes time to cool from millions of degrees down to temperatures where it can fragment and form stars. This cooling happens through atomic transitions, particularly hydrogen and helium lines, which radiate energy away into space. But what if the early universe contained more molecular hydrogen than we think? Molecular hydrogen cools gas far more efficiently than atomic hydrogen, operating at lower temperatures and radiating through rotational and vibrational transitions. If some process generated abundant molecular hydrogen in primordial gas clouds, perhaps through chemistry catalyzed by the first generation of massive stars, that could dramatically accelerate cooling rates, allowing gas to collapse into stars much faster than simulations predict. The second hypothesis invokes a fundamentally different initial mass function for stars. Today's stars follow a predictable distribution. For every massive star that forms, dozens of medium-mass stars and hundreds of low-mass stars are born. This initial mass function determines how much feedback a stellar population generates, because most feedback comes from massive short-lived stars that explode as supernovae. But perhaps the first generation of stars in these primordial galaxies was top-heavy, biased toward producing more massive stars than the modern IMF. Paradoxically, this could reduce effective feedback. If stars were so massive, they collapsed directly into black holes without exploding as supernovae. They would lock away their mass without injecting energy into the surrounding gas, allowing star formation to proceed unimpeded. The third hypothesis suggests that dark matter itself played a more active role than current simulations capture. Standard Lambda-CDM treats dark matter as perfectly cold and collisionless. interacting only through gravity. But if dark matter has even slight self-interactions, or if dark matter halos in the early universe were more concentrated than we model, the gravitational potential wells they created could be significantly deeper. Deeper potential wells mean higher escape velocities, making it far harder for feedback processes to blow gas out of galaxies. Even energetic supernova explosions might fail to eject gas from such deep wells, forcing it to remain within the galaxy where it continues forming stars. The fourth hypothesis is perhaps the most radical. Maybe feedback mechanisms genuinely hadn't established themselves yet in the first few 100 million years after the Big Bang. Modern galaxies regulate their star formation through a complex ecosystem of feedback processes: stellar winds, supernova shockwaves, ionizing radiation from hot stars, and energy output from active galactic nuclei. But each of these processes requires multiple stellar generations to become effective. The first supernovae need time to enrich gas with metals that enhance cooling and wind driving. The first black holes need time to grow massive enough to generate powerful jets. Perhaps there was a brief cosmic window, lasting a few 100 million years, when feedback simply hadn't turned on yet. During this window, galaxies could form stars with wild abandon, converting their gas reservoirs with 80% efficiency, before feedback mechanisms eventually established themselves and brought star formation under control. A fifth possibility, gaining traction among some theorists, is that baryonic matter, the normal atoms that make up stars and planets, was distributed differently in the early universe than simulations assume. Most models start from relatively smooth initial conditions at high redshift and let structure grow bottom up. But if the actual density distribution of gas in the early universe was lumpier, more clumped on small scales, that could seed the formation of massive galaxies directly, without requiring slow hierarchical assembly. Perhaps some rare, high-density regions acted as seeds for red monsters, allowing them to skip the normal bottom-up assembly process entirely. None of these hypotheses is mutually exclusive. The true explanation might involve elements from all of them. Hyper-efficient cooling combined with deeper dark matter potential wells, combined with temporarily absent feedback. What's clear is that solving the red monster crisis will require more than tweaking parameters in existing simulations. It will require fundamentally rethinking the physics of the cosmic dawn, potentially incorporating new processes that current models simply don't include. Perhaps the most compelling explanation for the red monsters is also the most unsettling. The early universe operated under fundamentally different rules than the cosmos we observe today. For the first few 100 million years, after the Big Bang, the regulatory mechanisms that govern galaxy formation in the modern era simply hadn't established themselves. The cosmic thermostat didn't malfunction. It hadn't been installed yet. The universe was running without brakes. Consider what happens in a modern galaxy when star formation begins. Massive stars ignite, blasting their surroundings with ultraviolet radiation that ionizes and heats nearby gas. Within a few million years, these massive stars explode as supernovae, injecting tremendous energy into the interstellar medium. This energy creates hot bubbles of gas that expand outward, disrupting molecular clouds and making further collapse difficult. If enough supernovae explode in a concentrated region, they can blow gas entirely out of the galaxy. This is negative feedback. Star formation triggers processes that suppress further star formation, creating a self-regulating cycle. But each of these feedback mechanisms requires time to establish itself. Stellar winds depend on massive stars forming and reaching their main sequence phase. Supernovae require those massive stars to exhaust their fuel and explode, which takes several million years even for the most massive population 3 stars. Radiation pressure from hot young stars needs sufficient stellar density to become effective. Active galactic nuclei feedback requires black holes to grow massive enough to generate powerful jets and radiation, a process that takes tens to hundreds of millions of years. In the first 400 million years of cosmic history, there may have been a critical window when none of these feedback processes had matured enough to regulate star formation effectively. The very first generation of stars, population 3 objects forming from pristine primordial gas, likely had lifetimes of only a few million years, but they formed in isolation, in small proto-halos scattered throughout space. Their feedback, while locally intense, couldn't propagate across large enough volumes to affect the next generation of star formation happening in neighboring halos. The second generation of stars, forming from gas slightly enriched by the first supernovae, found themselves in an environment where cooling was easier. Heavy elements radiate energy efficiently, but feedback was still weak. The supernova explosions from population 3. Stars. Occurring in low-mass halos with shallow potential wells, likely blew gas out of individual proto-galaxies. But that gas didn't disappear. It remained in the intergalactic medium, cooling and falling back into larger, more massive dark matter halos that were assembling through hierarchical mergers. This created conditions where massive galaxies, forming in the deepest gravitational potential wells, could accrete gas without effective resistance. The gas fell in, cooled rapidly through molecular hydrogen transitions and newly available metal line cooling, and collapsed into dense star-forming clouds. Star formation proceeded at extraordinary rates, hundreds of solar masses per year, without the regulatory cycles that keep modern galaxies in check. The result was hyper-efficient conversion of gas into stars, approaching 80% efficiency before enough stellar mass accumulated to finally trigger effective feedback. Webb's observations of early galaxies reveal this chaotic, unregulated state directly. The JWST deep field images show galaxies at redshifts 7 to 9 that are remarkably turbulent and clumpy, lacking the smooth, organized structures of modern spiral and elliptical galaxies. Gas within these systems moves chaotically, with velocity dispersions indicating violent internal dynamics. These aren't the calm rotating disks governed by orderly physics. These are galaxies in the throes of runaway star formation, assembling their stellar populations in brief, intense bursts before feedback mechanisms eventually catch up and bring the process under control. This feedback-free window might explain not just the red monsters, but several puzzles about the early universe. It explains why supermassive black holes appear so quickly. They grew during a brief epoch when accretion wasn't limited by radiation pressure pushing gas away. It explains why early galaxies are so dust-rich. Rapid star formation and supernova explosions created heavy elements quickly, allowing dust grains to form within the first few 100 million years. It explains why the epoch of reionization, when the first stars ionized the neutral hydrogen filling the universe, happened faster than models predicted. Star formation rates were so high that ionizing photons flooded the universe more rapidly than hierarchical assembly models suggested possible. If this hypothesis is correct, then the cosmic dawn was a brief, spectacular, violent era, fundamentally unlike any other epoch in cosmic history. It was a window when structure formation operated at maximum efficiency, unconstrained by the regulatory physics that would later slow everything down. The red monsters are fossils from that era, survivors that assembled during this feedback-free window before the universe learned to regulate itself. They represent not violations of physics, but revelations of what happens when physics operates without regulation, when gravity's pull faces no organized resistance, when the cosmic assembly line runs at full speed without safety mechanisms to slow it down. To understand why discovering massive galaxies at redshift 7 to 9 represents such a profound crisis, we need to grasp what redshift actually means and why it functions as a cosmic time machine. Every measurement of these impossible galaxies begins with a single fundamental observation. Their light has been stretched by the expansion of the universe itself. When a photon leaves a distant galaxy and travels across billions of light years to reach our telescopes, it doesn't travel through static space. It travels through space that's expanding, and that expansion stretches the photon's wavelength as it journeys. A photon emitted in the ultraviolet, with a wavelength of perhaps 100 nanometers, might arrive at Earth stretched to 800 nanometers, deep in the infrared. The photon hasn't lost energy to friction or collisions. The fabric of space through which it travels has literally expanded, carrying the wavelength along with it. This stretching is quantified by the redshift parameter, denoted Z. It's defined simply. Z equals the change in wavelength divided by the original wavelength. If a hydrogen emission line with a rest wavelength of 121.6 nanometers is observed at 973 nanometers, the redshift is Z equals 7. The wavelength has stretched by a factor of 8. The relationship is straightforward. The observed wavelength equals the emitted wavelength times 1 plus Z. A galaxy at redshift 7 has its light stretched by a factor of 8. A galaxy at redshift 9 has its light stretched by a factor of 10. This wavelength stretching directly tells us about distance and cosmic time. In an expanding universe, the farther away an object is, the longer its light has traveled through expanding space, and the more its wavelengths have stretched. But distance in cosmology is a subtle concept. We can define distance as how far light has traveled, the light travel distance, or we can define it as how far away the object is right now, accounting for how much the universe has expanded while the light was in transit. The comoving distance. For the red monsters at redshift 7 to 9, light travel distance is about 12.9 to 13.2 billion light years. But the universe has been expanding this entire time, so those galaxies are now about 30 billion light years away in comoving coordinates. More importantly, redshift tells us look-back time. How far back in cosmic history we're seeing an object. The red monsters at redshift 5 to 6 existed when the universe was about 1 billion years old. Objects at redshift 9 existed when the universe was only 550 million years old. At redshift 13, which JWST has detected in a few extreme candidates, we're seeing galaxies that existed just 330 million years after the Big Bang. Each redshift value corresponds to a specific cosmic epoch, calculated using the Friedmann equations that describe how the universe expands under the influence of matter, radiation, and dark energy. The relationship between redshift and cosmic age isn't linear. At low redshift, when the universe was already mature and expanding at rates dominated by dark energy, small differences in redshift correspond to large differences in look-back time. At high redshift, during the early universe when expansion was decelerating due to the gravitational pull of dense matter and radiation. Small differences in redshift correspond to relatively small differences in cosmic age. This compression of the timeline at high redshift means that galaxies at Z equals 7 to 9 represent a brief cosmic window, just a few 100 million years of cosmic history when structure formation was still in its infancy. Measuring redshift requires spectroscopy. When Webb's NIR-CAM GRISM disperses light from a distant galaxy, the resulting spectrum shows emission and absorption lines, bright and dark features at specific wavelengths corresponding to hydrogen, oxygen, carbon, and other elements. These spectral features have precisely known wavelengths measured in laboratory conditions. Hydrogen's Lyman alpha line, for instance, has a rest wavelength of 121.6 nanometers. When astronomers find this line in a galaxy's spectrum shifted to 1094 nanometers, they immediately know the redshift is Z equals 8, placing that galaxy about 13 billion years in the past. The significance of detecting red monsters at these specific redshift ranges cannot be overstated. At Z equals 7 to 9, the universe is less than 5% of its current age. In human terms, if the universe today is an 80-year-old person, we're looking at a cosmic toddler less than 4 years old. Lambda-CDM predicts that at this age, structure formation should be in its earliest stages. Small proto-galaxies just beginning to assemble, nowhere near the massive mature systems Webb is observing. Every photon captured from these red monsters began its journey 13 billion years ago, traveling across a universe that was expanding, cooling, and evolving. Those photons have been stretched from ultraviolet into infrared by the relentless expansion of space. They arrive at Webb's mirrors, carrying information encoded in their spectra, the chemical signatures of stars that formed when the universe was young, the redshift that tells us when those stars ignited, the luminosity that reveals how many stars existed. And that information is telling us an impossible story. Massive galaxies existed when they shouldn't, assembled with impossible efficiency, challenging every prediction about cosmic youth. The discovery of the red monsters and other impossible early galaxies isn't just challenging specific models of galaxy formation. It's forcing astronomers to rewrite the entire timeline of cosmic history. Events we thought took billions of years to unfold apparently happened in a few 100 million. Processes we believed were gradual and hierarchical now appear to have been explosive and rapid. The universe's infancy was far more precocious, far more violent, and far more efficient at building complexity than any theoretical model predicted. Consider the epoch of rionization, one of the most important transitions in cosmic history. After the Big Bang, the universe was filled with hot plasma, a soup of free electrons and atomic nuclei where light couldn't travel far before being absorbed. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This transition, called recombination, made the universe transparent, allowing light to travel freely. The cosmic microwave background radiation we detect today was emitted during this epoch. But then the universe entered the Dark Ages, a period when no stars existed yet, and neutral hydrogen fog filled all of space. This fog absorbed ultraviolet light, making the universe opaque to high-energy photons. The Dark Ages ended only when the first stars formed and began emitting ionizing radiation, splitting neutral hydrogen back into free protons and electrons, This epoch of reionization, when starlight gradually ionized the neutral hydrogen filling the universe, was thought to be a slow, gradual process lasting 750 million years or more, beginning perhaps 400 million years after the Big Bang and completing around 1 billion years. Webb's discoveries suggest this timeline was dramatically wrong. If massive galaxies with hundreds of billions of stars already existed 400 million years after the Big Bang, they must have been preceded by earlier generations of star formation, producing enormous amounts of ionizing radiation. The sheer number of photons required to ionize the universe's hydrogen fog means star formation must have been far more vigorous, beginning far earlier than previous models assumed. Recent analyses suggest the epoch of reionization lasted less than 500 million years and was essentially complete by 600 to 700 million years after the Big Bang, half the duration previously estimated. This compression of the timeline has cascading consequences. Population 3 stars, the first generation formed from pristine primordial gas, must have ignited earlier than we thought, perhaps as early as 100 to 150 million years post-Big Bang. These first stars lived fast and died young, exploding as supernovae and enriching their surroundings with heavy elements. That metal enrichment happened so quickly that by 400 million years, galaxies were already forming dust-rich, chemically mature stellar populations indistinguishable from later cosmic epochs. The rapid appearance of spiral structure provides another shock. Hubble observations suggested that early galaxies were mostly irregular, chaotic blobs of stars lacking the organized structures of modern spirals and ellipticals. Spiral arms were thought to develop slowly over billions of years as galaxies settled, their rotation curves stabilized, and density waves propagated through stellar disks. Webb has found spiral galaxies at redshift 4 to 6, existing when the universe was only 1 to 2 billion years old. Nearly 30% of galaxies at these epochs show clear spiral structure. Organization and complexity emerged far faster than hierarchical models predicted. The presence of mature chemical abundances in early galaxies further compresses the timeline. Spectroscopic analysis of red monsters and other high redshift systems reveals surprisingly high metallicities, abundances of elements heavier than helium that can only form inside stars. These metals require multiple generations of stellar evolution, massive stars forming, living briefly, exploding, enriching gas, and that enriched gas forming new stars. Cycles that should take hundreds of millions of years appear to have completed in just a few stellar generations spanning perhaps 100 million years. Black hole growth represents perhaps the most extreme timeline compression, as discussed earlier. Supermassive black holes with masses exceeding 100 million solar masses exist at redshift 9 to 10, just 500 million years after the Big Bang. Growing from stellar mass seeds to these enormous sizes, even at maximum Eddington limited accretion rates, requires 500 to 600 million years. The timeline barely fits, and only if black holes began growing immediately after the first stars formed, with no delays, no interruptions, no periods of quiescence. The universe apparently didn't waste time. What emerges from Webb's observations is a picture of cosmic dawn as a brief, spectacular, hyper-efficient epoch when structure formation operated at maximum speed. The first few 100 million years weren't a slow warm-up to the main event of galaxy formation. They were the main event, a cosmic explosion of complexity where galaxies, stars, black holes, and chemical enrichment all happened simultaneously in a compressed firework display. The universe's childhood was breathtakingly short. Adolescence began almost immediately. This revised timeline has profound implications for the conditions in the early universe. Rapid structure formation requires high gas densities, efficient cooling, and minimal feedback resistance. It suggests the early universe was a fundamentally different environment than the cosmos we observe today. Denser, more turbulent, more conducive to gravitational collapse and star formation. The red monsters are fossils from that brief window, relics of an epoch when the universe built galaxies at speeds we're still struggling to understand. The discovery of the red monsters marks the beginning of a new chapter in astronomy, not the conclusion. Webb has opened a door that reveals how little we truly understood about the cosmic dawn, and now the real work begins. Systematically observing enough early galaxies to distinguish between competing theoretical explanations and build a new framework for understanding rapid structure formation in the universe's first few 100 million years. JWST's observational campaign is far from over. The telescope is currently executing Cycle 2 and Cycle 3 programs that will dramatically expand the sample of well-characterized high redshift galaxies. Programs like Cosmos Webb aim to observe 500,000 galaxies with high-resolution near-infrared imaging, creating a comprehensive census of galaxy populations at cosmic dawn. The JADE survey, JWST Advanced Deep Extragalactic Survey, is pushing even deeper, targeting the ultra-faint galaxies that existed at redshifts beyond 10, when the universe was less than 500 million years old. These systematic surveys will determine whether the red monsters are rare outliers or represent a common galaxy population that standard models fail to predict. Critical questions remain unanswered. What fraction of early galaxies exhibit the hyper-efficient star formations seen in the red monsters? Is 80% gas-to-star conversion typical at cosmic dawn, or are we seeing exceptional cases? Understanding the statistics is crucial. If most high redshift galaxies show normal 20% efficiency, and only a few exhibit extreme behavior, that suggests special conditions or rare events. But if hyper-efficiency is common, that demands a fundamental revision of star formation physics in the early universe. Webb's spectroscopic capabilities will be pushed to their limits to answer these questions. Future observations will target larger samples with the NARSPEC instrument, which can observe up to 100 galaxies simultaneously using its microshutter array. These spectroscopic measurements will reveal detailed chemical abundances, stellar ages, and star formation histories. By comparing galaxies at different redshifts, snapshots at different cosmic ages, astronomers can trace how feedback mechanisms evolved and when they finally established themselves as effective regulators. But JWST cannot solve this mystery alone. Its strengths lie in infrared imaging and spectroscopy, revealing stellar populations and ionized gas. To understand the complete picture of early galaxy formation, we need to trace the cold molecular gas that fuels star formation, the raw material that collapses into stars. This requires observations at millimeter wavelengths, where molecular gas emission is strongest. Enter ALMA, the Atacama Large Millimeter Submillimeter Array in Chile. ALMA's capabilities complement JWST perfectly. The Crystal Survey, one of ALMA's flagship programs for studying early galaxies, is already revealing the distribution of cold gas and dust in galaxies observed just 1 billion years after the Big Bang. ALMA can resolve the internal structure of molecular clouds, trace gas kinematics through Doppler shifts, and measure the total mass of available fuel. By combining JWST observations showing where stars are forming with ALMA observations showing where gas reservoirs are located, astronomers can directly measure star formation efficiency and test whether early galaxies truly were converting 80% of their gas into stars. Follow-up. ALMA observations of the specific red monsters identified by Webb are already planned. These observations will reveal whether these galaxies still contain large gas reservoirs that will fuel continued star formation, or whether they've already consumed most of their fuel in a brief burst. They'll measure gas kinematics to determine whether red monsters are rotating disks, chaotic mergers, or something entirely different. And they'll trace the spatial distribution of star formation to see whether it's concentrated in compact cores or spread across extended regions. The next generation of ground-based extremely large telescopes will add another layer of capability. The European Extremely Large Telescope, with its 39-meter primary mirror, will provide spectroscopic observations at visible and near-infrared wavelengths with far higher resolution than JWST, allowing detailed studies of individual star-forming regions within high redshift galaxies. The 30-meter telescope and Giant Magellan Telescope will offer similar capabilities, creating a network of enormous ground-based facilities that can follow up on Webb's discoveries with unprecedented detail. Perhaps most importantly, theoretical work is accelerating. Simulation groups around the world are updating their galaxy formation codes, incorporating new physics suggested by Webb's observations. Some are experimenting with different feedback prescriptions, turning off supernova regulation in early epochs to see if that reproduces the red monsters. Others are exploring exotic initial conditions, lumpier gas distributions, more concentrated dark matter halos, different thermal histories for the intergalactic medium. The next few years will see an explosion of theoretical papers proposing, testing, and refining models that might explain hyper-efficient early galaxy formation. The path forward is clear, even if the destination remains uncertain. More observations will constrain the statistics of early massive galaxies. ALMA will reveal their gas content and kinematics. Updated simulations will test competing theories. Gradually, through the iterative process of observation, theory, and refinement, astronomers will build a new framework for understanding the cosmic dawn. The red monsters have shown us we were wrong. Now the challenge is figuring out what the right answer actually is. There's something profoundly humbling about standing at the edge of knowledge and realizing how little we truly understand. For centuries, humanity has gazed upward and asked the fundamental questions. Where did we come from? How did the universe learn to build the structures we see today? What forces shaped the cosmic landscape that eventually gave rise to galaxies, stars, planets, and ultimately to us? The James Webb Space Telescope has given us answers. But those answers aren't the comfortable confirmations we expected. They're revelations that force us to confront how much our elegant theories missed about the universe's actual history. The red monsters are more than astronomical anomalies. They're messengers from an epoch we thought we understood, carrying news that the cosmic dawn was nothing like we imagined. The early universe wasn't a patient, methodical architect slowly assembling structures according to the hierarchical blueprints we'd written. It was a creative explosion, a period of wild, unregulated, hyper-efficient structure formation when galaxies assembled in cosmic heartbeats rather than cosmic ages. The universe's infancy was more violent, more dynamic, more productive than our most ambitious simulations dared predict. This discovery echoes a pattern that repeats throughout the history of science. Every time we develop instruments powerful enough to probe nature at new scales, whether looking deeper into space, smaller into matter, or further back in time, we discover that reality is stranger, richer, and more surprising than our theories anticipated. The telescope revealed that Earth wasn't the center of creation. The spectroscope showed that stars were made of the same elements as Earth. Hubble's observations proved the universe was expanding, shattering the conception of a static eternal cosmos. And now Webb shows us that galaxy formation in the cosmic dawn operated under rules we never imagined, with an efficiency we can't yet explain. What makes this moment particularly significant is what it says about the nature of cosmic evolution itself. The universe we observe today is relatively calm, governed by well-understood feedback mechanisms that regulate star formation and prevent runaway growth. Galaxies evolve slowly, accumulating mass through mergers over billions of years. Star formation proceeds at modest rates, controlled by the balance between gravitational collapse and feedback resistance. But this calm, regulated state appears to be a late development, not the fundamental condition. The early universe was a different beast entirely, a cosmic frontier where structure formed without regulation, where feedback hadn't yet imposed order, where creativity ran wild before constraints were established. There's something almost poetic in this realization. The universe's childhood was its most creative period, the epoch when it built the foundations for everything that would follow. Those first few 100 million years, a tiny fraction of cosmic history, were when the fundamental architecture of the modern universe emerged. The massive galaxies that formed during that brief window became the seeds for galaxy clusters, the anchors around which cosmic filaments organized, the nurseries where generations of stars would forge the heavy elements that eventually allowed planets and life to exist. We are, in a very real sense, products of that violent creative burst at cosmic dawn. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in stars that descended from that first generation of hyper-efficient galaxy formation. The red monsters and their contemporaries created the chemical diversity that made complexity possible. They ionized the universe, clearing the fog of neutral hydrogen and allowing light to travel freely. They established the large-scale structure that eventually led to the formation of our own Milky Way. Without that brief period of unregulated, explosive creativity, we wouldn't exist. This confronts us with a fundamental truth about the universe. It's not obligated to make sense to us. The cosmos doesn't conform to our theoretical preferences or respect our computational limitations. It operates according to physical laws we're still discovering, through processes we're still learning to model, in regimes where our intuitions fail. The red monsters are teaching us humility, reminding us that 13 billion years of cosmic history happened without our observation, without our theories, without our approval. The universe did what it did. Our job is to figure out how, but this moment is also exhilarating. We live in an era when we can actually probe the cosmic dawn, when technology has advanced to the point where we can gather photons that have traveled 13 billion years and extract from them precise information about galaxy masses, star formation rates, chemical abundances, and cosmic ages. We can measure the properties of galaxies that existed when the universe was less than 5% of its current age. We can test our theories against observations of epochs no human eye could ever witness directly. We can watch the universe learning to build galaxies in real time, or at least in redshifted time. The red monsters have opened a new chapter in humanity's quest to understand cosmic origins. They've shown us that the early universe was far more capable, far more efficient, far more spectacular than we imagined. They forced us back to fundamental questions about how structure forms, how feedback operates, how galaxies assemble. And in doing so, they've reminded us why we explore, not to confirm what we already believe, but to discover what we never imagined. The universe is under no obligation to match our models. It simply exists, vast and ancient and full of mysteries, waiting for us to ask better questions and build better instruments and develop better theories capable of capturing its true nature. In the end, the story of the red monsters is our story. It's the story of a species that emerged from cosmic dust, developed consciousness, looked back across billions of years toward its own origins, and discovered that the universe that created us is far stranger and more wonderful than we ever dreamed. We thought we understood the cosmic dawn. We were wrong, and that wrongness is the beginning of wisdom.